Chapter 14, talking about chemical equilibrium, working on some of the concepts and then start working on the calculations. So basically, what is an equilibrium? Some of the reactions, if you have, for example, A going to form product B, this reaction goes back to form the A again. So some of the reactions seems like they stop before they complete. You expect all the reactant to change to the product, but you see after a while, seems like they both exist. None of them disappear. So we are going to find out what happens. This reaction is called reversible because A changes to B and then at the same time B changes to A. The example that you have on slide 14 is when you have carbon monoxide changing to methane and water in the presence of hydrogen. So you see we have the moles and we have the time. So we have 3 times as carbon monoxide for hydrogen, right? So if, for example, we say we have 3 moles of hydrogen and 1 mole of carbon dioxide, then the moles of carbon dioxide start depleting, they start decreasing by going towards the products, right? Also, the same thing for carbon, let's say this is carbon monoxide, this is hydrogen. And then, let's say for, let's say for methane, we had almost 0 at the beginning, right? The methane is the product. So by proceeding the reaction, you'll see, I should have made a better curve, it's not enough. So, see? So basically, in a nutshell, what this graph is telling us is that the concentrations of hydrogen and carbon monoxide, which were the reactants, is going to decrease eventually, and that of the concentration of CH4, which is the product, is going to increase, but they all get to the steady state, which is called equilibrium. You see, they are not becoming equal, but they all reach to the steady amount, which is called the equilibrium amount. So, if we want to describe the reaction equilibrium is the state where the rate of forward reaction becomes equal to rate of backwards reaction. So at equilibrium, rate of forward is equal to rate of backwards. That's what we have for equilibrium, chemical equilibrium. Now we can start working on the calculations. Let me adjust the board. All right. Let's work on the stoichiometry of equilibrium. PCl5 plus Cl2. This is the reaction we have on slide number 18. Then the question says, when heated, PCl5, phosphorus, and and PCl3 form. When 1 mole of PCl5 in 1 liter container is allowed to come to equilibrium at a given temperature, so we start with 1 mole of PCl5, the mixture is found to contain 0.135 moles of PCl3. 0.135 moles of PCl3. What is the molar composition of the mixture? So, we started with 1 mole of PCl5. At the beginning, before any product forms, we have 0 moles of any of our products. 0 and 0. But we started with 1 mole of PCl5. This is called the initial condition. Initially we have these. Then we let PCl5 to decompose, to change, to break down to PCl3 and Cl2. So during the change, something called X was subtracted from this amount, and the same amount X was added to both PCl3 and Cl2. Okay? So at the end, if you add initial and change to each other, we will reach the equilibrium state. So it's like we monitored the changes that the system goes through from initial towards the equilibrium. So at the end, we don't have the same 1 mole. Something has been subtracted from it. At the end, X plus 0 is X. Let me erase that. And then the same X has been produced for Cl2. So we call it an ICE table. I for initial, C for change, and E for equilibrium. So starting with 1 mole of PCl5 and no products in the system. Then you allow the PCl5 with the heat to break down. PCl5 starts breaking down to PCl3 and Cl2, so X will be subtracted, and at the same time products are produced, so X will be added to both of them. And the number, the coefficient for this X depends on the numbers that you see here, the coefficients. For this example, all the equations are 1, so X is just 1X. At the end, when you add these two, make sure you put the addition line. You will have 1 minus X, then X and X. The question said that at the end, PCl3 is 0.135 moles. So X is 0.135 moles. Because the X is the same for PCl3 and Cl2, so the same amount has been produced for Cl2. And how much has been remained? 1 minus amount of X, 0.135, which is going to be 0.85 moles. So one more time, system starts with only 1 mole of the reactant and 0 moles of products. It undergoes the change. X will be subtracted from PCl5 and PCl3 will have X amount and the same for Cl2 because the coefficients are all 1. Then we add the initial and the change for the system. So system reaches to the equilibrium. 1 minus X, X, and X. Don't forget this is the addition of these two. equilibrium state is the addition of initial and change. So we have 1 minus x, x, and x. The question says at the end 0.135 moles of PCl3 is produced. The same thing because both of them are x. The same amount for Cl2 has been formed, and what is left, what is remained from PCl5 is 1 minus 0.135, which is 0.87 moles. That's the composition of the system. So whenever you have questions about what is the composition of the system at equilibrium, means to report all the amounts for reactants and products at the end. So for each equilibrium, we can write an equilibrium constant. Equilibrium constant is the molar concentration of products to the power of their coefficients over molar concentration of the reactants to the power of their coefficients. So this is what you use to determine the equilibrium constant, which is called Kc. Equilibrium constant. Okay? Now, let's work on the example on slide number 24. And write the equation here. 2H2 gas plus CO gas is CH3 OH gas. So this is slide number 24. The question is saying methanol, also called wood alcohol, is made commercially by hydrogenation of carbon monoxide at elevated temperatures and pressure in the presence of a catalyst. What is the Kc expression for this reaction? So Kc expression, we said it's the ratio of products, molar concentration of products. You just have one product here. What is the power? 1, because the coefficient is 1. You don't write it. And 2, the molar concentration of reactants to their powers. H2, what is the coefficient for H2? 2. And for CO is 1. So that's how you write the expression for Kc. So let's work on another question to find the value of Kc with the real numbers. Okay, here is the equation. Carbon dioxide decomposes at elevated temperatures to carbon monoxide and oxygen at 3000 Kelvin. 2 moles of carbon dioxide is placed into a 1 liter container and allowed to come to equilibrium. At equilibrium, 0.9 moles of carbon dioxide remains. So remaining, or let me put it here, remaining is 0.9 moles of carbon dioxide. What is the value of Kc at this temperature? So initially, let's put we said the initial change and equilibrium table is called ice table. We just, this is an expression, we call it ice table. So let's build our ice table. Initially, we started with 2 moles of carbon dioxide, 0 moles of carbon monoxide, and 0 moles of oxygen. When it went through the change, the system went through the change, what is the coefficient here? You did not have only 1 mole of carbon dioxide, you had 2 moles. So 2x will be deducted. What is the coefficient here? 2. So 2x will be added to carbon monoxide, and because the coefficient for oxygen is 1, only 1x will be added. So at equilibrium, you have 2 minus, you're supposed to add this here, right? 2 minus 2x, then 2x, right? 0 plus 2x, and then x. The question, remember it said you have 0.9 moles of carbon dioxide left. So 2 minus 2x is 0.9 moles. Two minus 2x is 0.90 moles. So now we can find the amount for x, which is, if you do it, 2 minus 2x is 0.90, then x is going to be 0.55 moles. Now you can find the amount for carbon monoxide, which is 2 times 0.55, correct? It's going to be 1.10 moles, and for oxygen is just x, and x is 0.55 moles. So that's those are the concentrations. Those are the number of moles, correct? So you will end up having 0.90, 1.10, and 0.55. For Kc, what are you supposed to do? The molar concentrations of carbon monoxide to the power of 2, oxygen, and divided by carbon dioxide to the power of 2. These are molar concentrations, and these are the number of moles. But you are lucky here, because if you go back to the question, you had 1 liter. You had 1 liter. So the moles and the molarity are the same here. If the liter is not the same, then molarities are going to change. So go ahead and plug them in. Carbon monoxide, how much carbon monoxide you had? 1.10 squared. Oxygen, you have 0.55 to the power of 1. And you have, how much? 0.90 squared. So the value for Kc is going to be, I hope it's correct, I'm just copying from the PowerPoint slides, 0.82. Okay, that's the question on slide number 26. Yeah, that was slide number 26. All right, that's how you determine Kc from the values that you have before and after. So, one more thing about the equilibrium constant expressions. So far, if you go back to all the equations you had, everything was in the gaseous form. What if we have some water vapor solid carbon and carbon monoxide gas plus hydrogen gas. Whenever you are writing Kc, do not include the liquids and solids molar concentrations, because comparing to molar concentration of the gaseous compounds, molar concentration of liquids and solids does not change that much. So you can consider the molar concentrations of liquids and solids equal to 1. So if you write Kc based on what you learned, you have CO, you have H2, both to the power of 1 because there is no coefficient, H2O, and C. C is a solid, right? So its molar concentration is 1. So you basically just write molar concentration of carbon monoxide, hydrogen, both of them are gas, divided by H2O. So whatever you bring in the equilibrium constant expression should be in the gaseous form. We do not write the molar concentrations for solids and liquids because they are considered to be 1. Their change is very, very, very small and we can ignore it. Then one more thing that we need to know about let me give you another example of my own. Let's say we have CaCO3 solid and it's in equilibrium with CaO solid plus CO2 gas. So how do you write Kc for this equation? These two are considered to be 1, right? So Kc is just CO2, right? It's different, although you have 3 components, but 2 of them are solids, so they're just 1 and 1. So you just end up having the molar concentration of CO2. Interesting, huh? One more thing you need to know is when you have an equilibrium, let's say you have, and you call its equilibrium constant K1. What is K1? How do you write this equilibrium concentration? C to the power of C, D to the power of D, A to the power of A, and B to the power of B. If you reverse this reaction, let's say you have C and D as reactants, and you have A and B as products. So you call its equilibrium constant K2. Write K2. It's A, B, C, and D. So look at K1 and K2. Isn't K2 the inverse of K1? Doesn't it look like you have flipped it? So basically, whenever you invert or flip, reverse a reaction, its K is going to be inverse of previous reaction. Okay? This is what you keep in mind because it becomes very handy. And also, if you, let's go with the same example. Again, A and B form C and D, and the equilibrium constant is going to be K1. if the reaction is doubled, if you double all the coefficients, so K2 is going to be what? Okay, so it's going to be like this. It's like you have squared the previous rate, the equilibrium constant. So it's going to be K1 squared. So basically, whenever you multiply an equation by a factor, the equilibrium constant will go to the power of that constant. Okay? And finally, at the end of this video, how to change Kc, how to go from concentrations to pressures. If all the components are gases, all of them, that you write in equilibrium constant expression, if they are all gases, write the equilibrium constant like this, right? Okay, they are all gases. So instead of Kc, if you don't have the concentrations, you can go with Kp. That's the equilibrium constant based on partial pressures. And instead of molar concentration, use the partial pressure of C to the same power, partial pressure of D to the same power, partial pressure of A to the same power, times partial pressure of B to the same power. So that's the relation between Kc and Kp. And if you want to have a good relation between them, like let's say sometimes you can calculate Kc and you just have Kc, you don't know how to calculate Kp, then you have some calculations on the PowerPoint slides. Since I'm giving you this formula in the exam, I'm just introducing it to you. Kp, if you don't have this formula, Kp is Kc times RT to the power of delta N. R is the gas constant, 0.082 liter atmosphere per mole Kelvin. And delta N is the number of moles, the sum of number of moles of products minus sum of the number of moles of reactants between the two different sites. Now, let's work on an example that you have to make it more clear. CO plus 3H2 CH4 plus H2O, then all of them are a gas. So how do we write Kp? Since they are all gases, you can write Kp, and you can use the partial pressures. So partial pressure of the first product times partial pressure of second product. Both of the coefficients are 1, so we don't have an exponent. Partial pressure of carbon monoxide times partial pressure of hydrogen to the power of its coefficient. Then, if you would like to have Kc, you remember Kp is Kc times RT delta N. And what is delta N? You have the 4 and 2. And I guess I gave you made a small mistake. Delta N is N of reactants minus N of products. No, I had given you the right one. Sorry. It's always the products minus reactants. Okay, so it's going to be Kc RT over -2. So when you want to find Kc, it's Kp over RT 2, or whichever other coefficient, the equation form that you want to use. That was the question on slide number 37. And now you can calculate do the calculation on the question on slide number 38. CH3 OH gives CO plus H2O, H2, 2H2. They are all gases. What is Kp? By knowing that the value of Kc is 0.0952 at 227 degrees Celsius, but T is in Kelvin, so go ahead and add it to 273 right away. It's going to be 500 Kelvin, right? So your Kp is Kc RT delta N. What is delta N? 2 plus 1, 3 minus 1 is 2. So Kp is going to be Kc. The value for Kc is 0.0952, 0.082, 0.0821 liter atmosphere per mole Kelvin times temperature. Temperature was 500 Kelvin. So you can cancel Kelvin and Kelvin. Delta N is 2. So go ahead and do the calculations that these two to the power to the squared and times this. So Kp value at the end is going to be 1.60 times 10 to the second. All right, so work on equilibrium to the extent that you learned. Then in the next video we will work more on more concepts and more calculations.